try Teams again. Share. I'll share my entire screen, and only one screen, so that should make it easier.
Yes.
You see it now? Okay, good. Go back to here, slideshow, and weird that that shows up. Screen, yes, okay, good. I'm good to go? Okay. Good morning, everyone. My name is Francis Poulin. Please call me Francis. I recognize some faces here. Nice to see you again. See some new faces. Happy to have anyone here who decided to come. So thanks for coming. Today, so to introduce myself, I'm a professor in applied mathematics. I study physical oceanography, biological oceanography, and solar physics, as well as other stuff that comes up. I am also cross-appointed in physics. I teach a lot of courses in calculus, differential equations, continuum mechanics, classical mechanics, all sorts of fun stuff, which has a strong physical component, which I'm always happy to teach, and also the fun mathematics that goes along with it. Today, the title that I chose is The Physics of the Oceans, which has a lot of interesting physical problems that I can't possibly talk about all of them today. I don't know all of them, but I'm going to share some stories with you that I think are interesting. Feel free to ask me questions when you have them. I'm certainly happy to go on tangents. If I don't finish all of the slides, that's okay. I prepared some, but I'd rather make this worthwhile for you. So if there's something that you find interesting, you want to ask me about, by all means, ask me. And if I can say something intelligent about it, I will. If I can't, then I'll move along to something else. But to get things started, I'm going to show you something from windy.com, which I don't suspect many people have. Well, anyone here see windy.com before? Okay, so a couple of people have. It's beautiful. At the moment, what I'm showing you is the results of a simulation of the air currents over North America and part of the Atlantic. And you can tell lots of interesting things. So this is not real data, it's not real live data, but it's through a simulation, which is trying to predict things as accurately as we can, which is based on a fundamental understanding of the physical equations that describe the atmosphere, and a lot of hard work in terms of solving them accurately. So we can see that for the most part, there's a lot of winds going eastwards over Canada. It does show extreme temperatures, and there's lots of fun stuff to see here, which I'll come back to later on, maybe. But a particular feature that if you scroll really, really far down, you can find, which I want to find, is currents. So now you can see stuff that I get more excited about. The atmosphere is great. I love the atmosphere. I breathe it every day. But the oceans are things that I do like to study in terms of my research. And off the coast of North America, you do see that there is this very interesting feature going along the coast northeastwards, which is what's called the Gulf Stream. Something that is often talked about in the news in terms of climate is that the Gulf Stream slowing down. Is it ever going to stop? These are good questions to ask, and I hope to tell you by the end, I can't answer the question if it's slowing down, but I will hopefully answer the question, will it ever stop? Okay, and hopefully I can do that in 40 minutes, I was told. So the Gulf Stream is a very strong current that propagates water northeastwards, which is warm, starts off, well, at some point it's in the Gulf of Mexico. It transports warm water northeastwards, which is one reason why Europe tends to be warmer than, say, North America, because of the warm transport of water. And the Gulf Stream is great, but there's nothing really special about it besides the fact that we're adjacent to it. If we go, oh, can I do this? I'd like to make it smaller. There's a zoom button here, I presume. Okay, so I can't do that very easily. If I switch oceans, I go from the Atlantic to the Pacific Ocean. I want to find Japan. Off the coast of Japan, you see something that looks kind of similar. It's called the Kuroshio current, and it also propagates northeastwards along the coast and then separates, but now mostly goes eastwards. So it's a very different creature, but it has the same physical mechanisms that generate it as the Gulf Stream. And if I were able to scroll more easily to the Southern Ocean, I could show you 3 other examples in the Southern Ocean, one off the coast of Brazil, one off the coast of Africa, and one off the coast of Australia. If you're better able to go through windy.com, you can probably find that. And one of the things I want to explain today, besides why oceanography is fun, is why do these things exist the way that they do, and maybe answer the question as to whether they will ever stop in our lifetimes. Questions or thoughts so far? Yes?
And this is the particular from the surface of the ocean.
So this is, the arrows are showing the velocity, the color, I believe, well, it's in the bottom right. I think the color is showing us the temperature, I believe. But I don't know windy.com very well. I just go to it for the pretty pictures. And sometimes it's nice to see where the winds are going, but anyhow, you've seen it. If you want to play with it, you are welcome to do that. But I will then go back to my talk. And I want to give you a short history of oceanography, because I imagine it's a field that you probably haven't seen very much in any of your physics courses, because I certainly didn't see it when I was a student in Alberta. Saw a lot of interesting physics, but not necessarily oceanography, which I didn't think of as being physics until graduate studies. But I'll give you some history of that, talk about the atmosphere, because the atmosphere is also very interesting, and of course, intimately connected to the oceans because they touch. The atmosphere and the oceans exchange a lot of properties. I'll talk a little bit about the general structure. I'll talk about the oceans, and then I'll talk about western boundary currents if time permits. And I probably won't have time for conclusions because I'm sure that I won't have time for it. So, history of oceanography. So, cover about 2/3 of the Earth. So clearly they're very important. It's a huge, well, they are a huge resource for food and natural resources, like sushi, for example, or whatever else. One important part of the ocean is that it acts like a heat sponge for the atmosphere. And the ocean actually contains a lot more heat than the atmosphere ever can, which is why if we wanted to stop the warming climate, it can't happen very quickly because of the fact that there's already so much more heat in the ocean. So it would take about 10 years for things to start to slow down because of how much heat is already there. In terms of oceanography, physical oceanography in particular, it's a fairly young science, less than 100 years old. At the beginning, before that time, it was mostly descriptive. People took boats, they knew where the currents went, they used those in order to plan their trajectories. They needed to for trade and things like that, but it wasn't really quantitative to the same degree as it is today. And now it is a quantitative science. Meteorology and oceanography are very similar fields. Meteorology tends to be ahead by maybe 10 years because people want to know the weather outside more so than knowing the weather in the oceans, which is very practical. And meteorology is also a very challenging subject. One thing that it doesn't face that oceanography does are coastlines. So there are some differences, but a lot in common for sure. And even though we do collect a lot of data, and when I say we, I mean my peers, I'm not an observer, but there are a lot of satellites, a lot of cruises, a lot of gliders in the oceans measuring all these things. There's still a lot that we don't see that we can't measure because the oceans are so vast. Which is why using simulations gives us a lot more data, but need to keep in mind that it's not really the oceans, it's our prediction of what the oceans could be doing. So every field has a pioneer. For physical oceanography, I would leave that in the hands of Henry or Hank Stommel, who only has a bachelor's degree or had a bachelor's degree from Yale in astronomy. So went from astronomy to oceanography, which at the time wasn't really a science. He did really make physical oceanography a science, which it still is today. He explained why we have the western boundary currents that I showed you today, like the Gulf Stream and the Creatio. He was the first person to put a theory to say why these things happen. There's still a lot of questions even today as to the details, but he clearly had great physical insight. He also talked about the theory of the thermocline, which I'll mention maybe slightly later on, but not very much. But his great physical understanding led him to create these theories, and he didn't, I was told, that he didn't have a vast knowledge of mathematics, but at the same time, he learned the mathematics that he needed when he wanted to understand something physically. I'm all for knowing as much mathematics as you can, but there's sometimes when you don't know enough math, when you want to understand a physical problem, you need to work harder and learn the math. Sometimes you have to create whole branches of mathematics, which mostly happens in pure math, but there is always a strong connection between these two. The more physics and math you know, I think the more you're able to describe and understand the world around us, which is something that people who've taken classes with me know that I certainly try to encourage as much as possible. So that's a very brief introduction to history of oceanography, but all that I have time for today. And I should say that I've described oceanography as a very quantitative science, and it is. I could bombard you with many equations in this talk, which I probably did in previous years. I'm not going to do that. I've learned that, well, I was told this is for a general audience, and I know there's students here who are in their first year, so I don't want to bombard you with equations that you may not understand. I'm instead going to focus on trying to share physical understanding with you and show the basic ideas without necessarily going into all the details. I think I'll only show you 6 equations, which in the past I've only shown 6 equations per slide. I'm trying to show some restraint because I think this would make for a funner talk. I see people nodding. Good. Okay, so I guessed right on that one. So the atmosphere consists broadly of 5 different layers. And we live in the troposphere, which is the first, I thought it was 10, they say 12 kilometers, so they're probably right. This is where we live and breathe. Planes basically travel at the top of the troposphere. When you go up, you have all these different layers. And I'm not going to talk about the atmosphere in detail, but just to realize there's a lot of variation from layer to layer. Interesting stuff happens. Where we live in the troposphere, we can measure, this is a measure of, an average measure of the temperature in the atmosphere as a function of latitude. Equator is the center, North Pole is to the left. That's weird, but South Pole is to the right, not used to that. And the ground is at the bottom, and at the top, we're around maybe at the top of the troposphere, which we call the tropopause. And clearly, it shows us something that we already know, that guess what? The tropics are warmer than the poles, which are really cold. And across the surface of the Earth, there's a huge gradient in temperature. When you go further up, you see that the temperature is actually pretty uniform at the top of the troposphere, and it's all basically red. So it's like, what does it say, 500 or something degrees Kelvin? So it's warm, but the variations we experience on the ground kind of get forgotten or start to dissipate away, and we do have much more uniform behavior because we live in what you could call a boundary layer. The surface of the Earth is a boundary layer, and things are interesting along this boundary. You go further up from this, and it doesn't really notice the details of what's going on Earth. So, pretty picture, and it is averaged over all the lines of longitude. So, what I want to focus more on, a bit more dynamics, and we're all physics-minded people here, so we'll start talking about more physics, is that the atmosphere actually has six atmospheric cells, which is interesting. And why it's 6, I'm not going to be able to answer. It's a harder question, but to understand what happens, so in the cells near the equator, so I'm going to focus mainly on the northern hemisphere because that's where we live, that's what I understand, but there are real parallels from northern hemisphere to southern hemisphere. And to understand what happens, basically, if we're at the tropics, we know that the tropics receive much more heat than the poles. We saw that previously. We saw the results of that previously. So at the tropics, when the ground is warmed by the sun, what does warm air do? It's going to tend to rise. So you do have this rising of the air. It'll rise for a while, but at some point it does start to diverge, going, part of it will go towards the northern hemisphere, part of it will go towards the southern hemisphere, which is, do I have a cursor here? So showing the rising over here and then the spreading. So it's going to spread. If the Earth weren't spinning, well, we wouldn't be here talking about it, but if the Earth weren't spinning, it turned out we just have one cell in each atmosphere. Because of the rotation of the Earth, it turns out that we have three. So at some latitude, which they're showing here is about 30 degrees, the air, which is very high up, gets cooled and it starts to fall. So we have the lowering of the air towards the ground. When it gets to the ground, it tends back towards the tropics. But as it does, the rotation of the Earth creates what we call a Coriolis force, but is really a pseudo force, which in the northern hemisphere deflects things to the right. So when the air is propagating from 30 degrees north back towards the equator, northern hemisphere deflected towards the right, which means that it's going to generate winds that'll have a westward component in the tropics. Southern hemisphere, it's deflected towards the left, which is why you still have a westward component. So near the tropics, or in the tropics, from minus 30 degrees to 30 degrees, you have a strong westward flow because of the Coriolis force. If you consider the other cells, where we have the lowering of the cells at 30 degrees, well, there is a splitting. The part that heads towards the north is also going to be deflected towards the right, but that means it's now going eastward. So that's why at our latitudes, the prominent winds are going eastward, whereas in the tropics, the prominent winds are going westward. And if you go more towards the poles, it'll change to the other direction to be westward. So we do see that there's this transition of the westward, eastward winds because of these cells and because of the Coriolis force. Yes?
Does that have anything to do with like hurricanes being formed around that area?
Hurricanes.
Because of the transition and kind of cause a rotational?
Those tend to be much smaller scale, so they would certainly happen in the atmosphere, but I don't think, well, and they do feel the Coriolis force because of how large they are, but I think that would be more of a separate phenomenon. But hurricanes are not things that I understand very well. I understand vortices, but not those particular vortices, but I think that's a slightly different phenomenon. Other questions? Okay, so I'm not sure if this is all very well known, but I've tried to explain in 5 minutes or so why we have winds appearing the way that they do on the Earth, which I didn't explain it in great detail, but hopefully I've given you the idea, which is interesting, I think, understanding the basic dynamics of the atmosphere, but also imperative to understanding the western boundary currents that we're going to talk about later on, I promise. So not on Earth, Jupiter, which I almost studied in my PhD, is a very different planet, much larger. One thing it's very well known for are the beautiful bands that you see, which are much clearer today than they ever were because of the recent photos that were taken. And each of these bands corresponds to a cell. So on Earth, we have 6 cells. If we were from space, it wouldn't quite look so nice because the chemical composition of our atmosphere is very different from that of Jupiter. But each of these bands corresponds to a cell. And you have that these cells are changing from westward to eastward. There's very strong shear in between, and this strong shear can generate vortices. Whether they become hurricanes or something else, I don't know, but there's a strong shear which does generate things. The great red spot, which you can see towards the upper left part of the picture, is a large vortex which has been there for possibly 300 years, at least 300 years it's been observed. And that's a very big vortex, not the kind that have generated these bands, but a lot of interesting dynamics, but I want us to focus on Earth. But I could not talk about that because I like showing pictures of Jupiter. So we've talked about the atmosphere very briefly. I now want to talk about the oceans, which is of course why we're all here. And the oceans, I'll give you a very brief overview. The average depth of the oceans is about 3.7 kilometers, maximum depth that we know of. is around 10 kilometers, maybe there's more. If you were to find the total mass of the ocean, it would be 1.4 times 10 to the 21 kilograms. Heavy, 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 which puts a lot of weight on the Earth. The atmosphere is smaller, is lighter by a factor of 3 orders of magnitude. So the atmosphere is a lot bigger. We saw it went up hundreds of kilometers. The ocean much shallower, but much heavier because water is heavier than air. Nothing too surprising there. Oceans certainly change in time because of plate tectonics. This is where we're at today, but it'll change in certainly a lot more years. One thing that I heard about a while ago I didn't know is that apparently there were no oceans on Earth before 3.8 billion years ago. Now we have a lot. We have 10 to the 21 kilograms of water, which form the oceans. If there were no oceans before and there are oceans now, how do you think the oceans appeared? There weren't scientists there adding it, but certainly there must be a scientific explanation. Not my area of expertise, I'm going out on a limb here, but any thoughts as to how oceans would suddenly appear? You answered the question already, so. Could be. I'm not sure if there was a huge change in, well, the Earth certainly has big temperature changes throughout the times. I don't know that the temperature changed a lot at that time. I don't think that was necessarily the cause, but maybe. Comets, meteorites, basically fell from the sky. Not in one fell swoop, but meteorites that come to Earth, if they have ice on them, ice will then arrive on Earth and then melt, and a lot of water would have to fall, 10 to the 21 kilograms of water, but that's a theory that people have proposed as to why we now have oceans on Earth, whereas when the Earth was still formed, there were none. I don't know if it's true, but I think it's really cool. And I couldn't help but share it with you. And a lot of the ocean is liquid, but of course, a lot of the ocean, part of the ocean is actually frozen, about 2%. And that, of course, is changing and changes with the seasons, changes year to year, and changing much more now than it ever was because of climate change, which I'm not going to talk about today, but it's certainly something well worth talking about. So similar to the plot that I showed you before of the temperature in the atmosphere, this is a comparable plot for the temperature in the oceans, where again, equator is the center, north is now towards the right, which is more comfortable for me, south is towards the left, but it doesn't really matter. And this is again, this is in the Atlantic Ocean, I think, averaged over lines of longitude, and no surprise, the tropics are warmer than the poles. Yes, so this makes sense. It looks almost like it's the inversion of the atmosphere, and it kind of is. But one thing I want you to realize is these are lines of constant temperature, which is very much correlated to the density. So let's say the density between friends. These lines, so if we go towards the center in the tropics, the lines are horizontal, which is what I would call, which is nice and simple. But when we go away from the tropics, we go towards either the South Pole or towards the Southern Hemisphere, say South Pole or the North Pole, these lines get tilted. So I'm clearly more excited about this than you are, or more interested in this. And why do I think this is interesting? Well, when would you observe lines of density that are basically like that? So this isn't a steady state. The oceans are ever changing, but the mean behavior of the oceans does have these tilted density surfaces. There's a lot of potential energy associated with that. How can these huge masses of water have density surfaces that are tilted like that? Why don't they just fall? Because if I have water in my sink, and if by some miracle I manage to have warmer water sort of in a U shape, and I just let it go, it's going to flop. And it'll oscillate around there, sure, but it's hard to maintain this amount of potential energy, but it does happen in the oceans because of something called thermal wind balance, which I'm not going to talk about today. But what's amazing is that you can have these sort of profiles in a steady state solution if where you have a horizontal gradient in the density, as long as there is a sufficiently strong vertical gradient in the horizontal velocity. So everywhere you see the density change like this, what I'm not showing you is the velocity, and the velocity has a shear, and there's just the right balance where you can achieve that these lines of constant density are tilted, and it can be a steady solution, but there's still a lot of potential energy. And when things happen in the ocean, there's a lot of potential energy that can then be extracted and converted to kinetic energy to create things like vortices and other interesting things in the ocean. So there's a lot of energy here, which goes on all the time, which is in a realm that we don't normally, it's hard to understand at first because we don't really have intuition with these large scales. We're used to water in a sink, maybe water in a pool, maybe we go to a lake, but this is huge. And because of the rotation of the Earth, the dynamics is quite different. And so there's a lot of interesting behavior that happens, which I still find fascinating after decades, which we understand to some degree, but it gives rise to a lot of different dynamics that we don't necessarily understand all of. So there's still a lot of work to be done. So in terms of the oceans, it can roughly be divided into two different sections. So there's the dynamics in the horizontal, which is the quasi-horizontal part, which I'll be talking about today, which creates things like ocean gyres, which I'll mention later on. There's also the vertical exchange, or the vertical structure, which is called the meridional overturning circulation, which I won't talk about very much. But you do have water being transported through the oceans. This figure here is trying to show in red where you have transport near the surface, in blue where you have transport near the bottom, and the transition between the two is where you have, well, when you have red to blue is where water is sinking, and where you have blue to red where water is rising. Now, one interesting thing to note is that this isn't necessarily saying this is the only place it happens, but this is the prominent regions. There's a lot of transport around the surface of the ocean, on the bottom of the ocean. There are very few places where you have water going from the surface to the bottom. In this plot here, we only have one, which is in the North Atlantic, and there's only two places where we have the water rising from the bottom to the surface. Now, why would water sink? Well, it's because it's more dense. Density is determined by the temperature and the salinity. So in the North Atlantic, we have that it's cold. If it gets colder, the density of water near the surface is going to decrease. If it gets saltier for whatever reason, then the density could also decrease. And that's a simple way to understand why water could fall from the surface of the ocean down to the bottom, because it has lowered its density, so it's lowered its buoyancy and it sinks. What causes water at the bottom of the ocean to rise? Think about that for a second. And this is called the ocean conveyor belts, which is very idealized, but it does show us roughly how water is transported to the oceans, and there is a global cycle. I think the whole cycle is estimated to be around maybe 100 years. The Earth is big, the oceans are vast, so there's a lot of distance to travel. So this is trying to show you the different gyres that appear in the ocean. I mentioned this before I showed you the Gulf Stream, which corresponds to this gyre in the North Atlantic. I showed you the Kuroshio with thanks to windy.com, and there's an ocean gyre here. But in the southern hemispheres, we also have a Brazilian current, which is going poleward, which has a gyre. There is East Australian current over here, which is also going poleward. There is the Agulhas current. So these 5 gyres each have a western boundary current, and the motion is predominantly horizontal. So the vertical dynamics is, of course, important, but I'm just going to focus on the horizontal dynamics and try to understand that in the time that we have left. And this is a very busy plot, maybe too busy, that tries to show how we have water moving from, we have the north towards the right. This is the Arctic water, which, as I mentioned, because of temperature and salinity, it can become denser, it can lower down at a particular level of buoyancy, particular height where it's not wanting to rise or fall. It'll be very happy to be at this level unless something happens to change its density. When you go toward the Southern Ocean, you see that there is a tendency to rise. And it's really not entirely well understood by me, but even by the community, as to what happens to cause the cool water at the bottom of the ocean, or even the center of the ocean, to rise, because it has to either become warmer or less salty. And there are not a lot of mechanisms that are going to be warming water at the center of the oceans. There are things like wave breaking, which colleagues of mine like Kevin Lamb and Mark Stasna study, which are one important process that do contribute. But just to say, this is something that is something this interesting mystery with you. Okay, so in the 10 minutes or so I have left, I want to talk about western boundary currents. So I said I have 6 equations, half of them are on one page. And I'm not going to show you where they come from because that would take a whole lecture, but you've all seen classical mechanics, you've all seen Newton's second law. There is an analog for Newton's second law for water, which is not a particle. Well, technically it is a bunch of particles, but we approximate it as a continuum, as I teach in AMath 361 this semester on continuum mechanics. But the version of Newton's second law for a continuum looks like what I have here, where instead of the mass times the acceleration, it's the density times the total derivative of the velocity, which is like the acceleration, but I have the big D instead of a little d for the derivative because it's following the fluid. So the density times the acceleration following the fluid is equal to a sum of the forces. In words, I hope that that can make some sense, even though I'm not showing you exactly what the big D is, but there is an analog. There's also an analog of conservation of mass, because if you have water in a container, you try to squish the container, well, mass has to be conserved. It turns out, using vector calculus, which many of you have not seen, I apologize, you can describe that by saying that the divergence of the velocity field is 0, and that ensures incompressibility. And because of thermodynamics being important, again, it's really talking about the change of the density following the flow, which in the absence of any heating or anything would be conserved, but can change because of sources. So I'm just showing you the basic ideas based on what you understand from classical mechanics, and the details are certainly more complicated, but this is the starting point and the basis for many studies of oceanography, meteorology, solar physics, a lot of other interesting things that go on. If you want to hear this, I can talk about it later on, but I'll just say that the same physical principles do exist, but we need to describe them for a continuum, which requires a bit more work. Now, because things tend to rotate, angular momentum is important, but the angular momentum for a fluid is more complicated than that for a particle. For a particle, it can spin, well, I guess a three-dimensional object can spin in X, Y, or Z directions. If you have a fluid which can change shape, and it often does, what we talk about is the vorticity. Vorticity is something I don't expect people would have seen before, which is fine. It can be defined as the sum of the rotation of 2 orthogonal lines. So I have a picture here from my course notes from AMath 463 in fluid mechanics, where I have 2 orthogonal lines. Say this is the unit vector in the x direction. This is the unit vector in the y direction. If I have a velocity y2, which is in the y direction, applied here and applied there, using Taylor approximations, assuming these are close to each other, then the difference in the velocity on this side is proportional to the x derivative of the y velocity. And if this is positive, it's going to cause the right part to go upwards, which is going to cause it to rotate counterclockwise, and we call that positive vorticity. Similarly, along the y-axis, if there is a velocity, on the y unit vector, if there's a velocity going in the x direction on the bottom and a different velocity on the top, which has the partial derivative of that x velocity with respect to y, if that's positive, it's going to cause things to rotate, but it's then going to rotate in the clockwise direction, which is opposite. So in order to have them summed up in the right direction, we define the vorticity as essentially the x derivative of the y component of velocity minus the y derivative of the x component, and that gives us an idea as to how things are rotating around the vertical direction. So it's a complicated idea. I'm not doing it justice, but I want you to realize vorticity is really angular momentum, but we need to talk about something more than just the standard expression for angular momentum, because we do have things moving around. Okay. And vorticity can be conserved in the same way that angular momentum can be conserved, but can also change because of stuff like torques acting on it, but torques, which is the analog, which we need the analog of for continuum mechanics. So one big thing that I mentioned already is the Coriolis force. And the Coriolis force is really due to the rotation of the Earth, and it's due to the rotation vector is going through almost the center of the Earth, not quite. And often, because even though the Earth is a sphere, I know it's a sphere, because we usually measure things locally, not over the entire globe, it's very convenient to measure things in a Cartesian coordinates at any particular position. So we talk about eastwards being x, northwards being y, and upwards being z. And we talk about the northward component of the Coriolis parameter, which is really the projection of this vector here at our particular latitude in the upward direction, and it's maximal when we're on the North Pole, if we're over there, because it's going parallel to it. When we go down toward the tropics, the upward component is 0 because it's all in the northward direction. So what I'm trying to show with this is that there is a Coriolis force that appears, the strength of which is determined by the northward component. And this is something that does change with latitude because the Earth is spherical. If the Earth was flat, it wouldn't change at all. It would be constant. But the Earth is not flat, so life is more interesting. And as I'll say later on, this is connected to why in the Atlantic, near the Gulf Stream, most of the water flows towards the poles. So I mentioned the winds, and at the beginning I showed you windy.com results, and this is trying to show this in a similar way, but this is from some previous study. And in the North Atlantic, we do see that there are what they call the prevailing westerlies, which are coming from the west, which have a strong eastward component. But near the equator, we have the north trade winds because they were used for trades back in the day, which go westward. So we do see that there is water going eastward towards the north, westward towards the south. If I were to put a paddle between those two, it would rotate in a clockwise direction. I said clockwise direction corresponds to negative vorticity. So the winds blow on the ocean, they do drag it along, they add energy, but they also add vorticity. And because a paddle would rotate in the clockwise direction, the winds over the North Atlantic are adding negative vorticity into the oceans, which is causing things to rotate in a clockwise direction. If there wasn't any continents, they would just happily flow in opposite directions, but there are continents, so when you have things going against continents, water doesn't beat rock, something has to happen. What happens? So another important ingredient to understand the Gulf Stream is dissipation. And this picture isn't necessarily ideal, but I thought it was pretty, so I wanted to. There are different kinds of. The ocean is rubbing against the bottom of the ocean, which causes bottom drag. The oceans are going along the coastlines, which is causing, there's some lateral viscosity, which is causing things to dissipate. There's also the motion of the molecules, but that's something that we can't really include on these ocean models because the molecules are tiny. The models go down to maybe 1 kilometer if we're lucky. So there is some sort of viscosity. Actually describing what the viscosity is an ocean model is the hardest problems we have in the field, which we're not doing right, but we have to do something. And the western boundary currents, I mentioned this already for the sake of time. No, I do have to talk about this. So I've talked about how in the North Atlantic, near the Gulf Stream, we have the winds driving the water towards the east. Towards the south is going to be driving the water towards the west. Because of the curvature of the Earth, we're going to show that this is going to induce equatorward flow. So if you have equatorward flow in most of the North Atlantic Ocean, well, it doesn't actually go through the tropics. It actually does come back. And the question is, if it has to come back in this region, does it come back to the west or does it come back to the east? What we've observed in windy.com and many of the pictures I've shown is it comes back in the west. But it comes back in the west on all the ocean basins. It never comes back in the east. Why is that? That's what I'll hopefully explain in the next couple of slides. So the conservation of potential vorticity, so these are, I think, the last two equations I have to show you. In the same way that you can have an equation for the evolution of the angular momentum, you can have the evolution of the vorticity, which has two basic parts. There is the vorticity due to the fluid, which can be spinning. This water can spin around like that. But there's also a contribution from the rotation of the Earth, which is what we call the planetary vorticity. And the sum of those two gives us the total vorticity in the vertical direction, which would be conserved when there's no forces acting on it. But we've said there are winds. Winds are blowing, which are adding negative vorticity into the North Atlantic. There's also dissipation going on. So clearly they're not conserved. If we look at the interior of the gyre, where the velocity becomes very, very small, vorticity becomes very, very small, dissipation isn't important in the interior. It's really important near the coastlines. We have a near balance, which says that the material derivative of the planetary vorticity, which becomes beta v, where v is the velocity in the y direction, is equal to really the curl of the wind. So the rotation of the winds, let's say. And because the rotation of the winds is negative, as we've described, v is negative, so we have flow going towards the equator. In the southern hemisphere, basically changes directions. Flow is still going towards the equator, but from the south. So this talks about what's going on the large-scale gyres, but what happens because of the western boundary current. Well, this is describing things locally, so a local conservation law as to what happens at every point. If we want to talk about the global, we should integrate the entire domain, but the other and looking for possible steady solutions. The other terms involving the derivative don't really contribute because they move things around. They don't really generate a net part of vorticity. But the forcing that's the forcing that is being applied to the oceans does tend to nearly balance out, meaning there must be a balance between the winds and the dissipation. Because of the fact we mentioned the winds adds negative vorticity, the total contribution from the double integral or the sum of the winds will be negative. For this to sum to zero, it's only possible if the total contribution from the dissipation is positive. So this is the key result to understand why we have western versus eastern boundary currents. I've drawn very poorly two scenarios that could occur. On the top, we have the case of a western boundary current, which is what actually happens. On the bottom, we have the case of an eastern boundary current, which doesn't happen. And I've put this red horizontal bar here to denote a paddle. And when I look at the eastern boundary current, I put a paddle here. What direction is it going to spin? Well, because the velocity is faster on the left, it's going to spin clockwise, meaning it has negative vorticity. So the vorticity induced by dissipation, if you had an eastern boundary current, would be negative, but you can't have negative plus a negative yielding some sort of balance. So this is why that can't happen. If you have this paddle on the western boundary current on the left, which is close to the wall, which is where the dissipation occurs, it rotates in a counterclockwise direction, which is positive vorticity. So the dissipation basically adds positive vorticity, which cancels out the negative vorticity that's added by the winds. So a very simple argument. I'm not really doing it justice, but it's one simple way to understand why western boundary currents occur always, because it's the right sign of vorticity to balance the winds, whereas the eastern couldn't possibly do that. And though I guess I've gone longer than I should have, my apologies. I don't really want to read out the conclusions. One thing I will say in terms of, will the Gulf Stream ever stop? The three essential ingredients that I've said as to what maintained the Gulf Stream are: one, the curvature of the Earth. Not going to. Second is the winds blowing, and the winds are not going to stop. The winds can change, but the winds are not going to change their mean directions anytime soon. And the third is some kind of dissipation. So if you have these three things, you will always get western boundary currents as long as the winds blow, the Earth turns, and dissipation exists. So it can slow down, which can have big impacts on the oceans and on us, but they shouldn't stop as long as these three things continue. And I've gone too long, my apologies, but thank you very much for your time. Happy to answer any questions you might have, or try to answer any questions you might have. Yes?
You talked about wave breaking and how that might be why water is rising.
One mechanism, wave breaking is one mechanism that can change the buoyancy of water and cause it to be more buoyant to then rise. One that I know of, yes. Yes?
Are hydrothermal vents, and say, like, I guess just like sources of, like, I guess like the insides of the Earth, like, could those not heat up the water from inside the Earth?
They certainly could, and I'm sure that they do play a role in this particular example. I don't know whether there are any hyperthermal vents in this region. It is near topography, which is one reason why I mentioned the internal waves. Certainly hyperthermal vents, if they can have some lasting effect to this height, they could contribute as well. Agreed. Is there someone else who had their hands up?
I had the same question.
Okay, so yes, I'm sure they contribute to some degree. I don't think they're necessarily the main factor, but the closer they are, the more they would contribute. Yes?
About the rotation of water. So when water is rotating, so where does the water go? We just go on the ocean and
So this is talking about the water that sinks from the surface to the bottom, for example?
No, the rotation of water.
The rotation?
Yeah, so when something is rotating, it causes centrifugal force. So water would naturally lead to the center.
Right. Right, so there is a centrifugal force, and if I can find the plot of the Earth, which I guess is later on, so this one here. So the Earth is rotating, and because the Earth is rotating, I've only talked about the Coriolis force, but there is a centrifugal force that is created as well, which is also interesting, because of the fact that it's the distance from the center that's going to be determine how strong it is. Sorry?
I mean, for the divisional rotation, because I read the way up graph where there's part of the Earth where the water is rotating.
Showing the rotation of water. So the rotation of the water that I've shown you is mainly spinning around the vertical axis. So it's spinning in the horizontal direction. So it's kind of going in a circle in the horizontal is one example that we can do that, but it's predominantly in the vertical direction. You can have that it's tilted, which can also transfer the vorticity from the vertical direction to the horizontal, but that's something a bit further. Any last questions? Yes?
Are you planning on teaching any classes in the spring as it stands?
No. I love to teach, but also need to get some research done. So this spring I'll be doing some research. Okay. Well, thank you all for your time. I wish you all well and enjoy the weekend.